Hi, so thank you for the opportunity to present this work. So this is effectively a model to predict the wildfire activity on a probabilistic basis, which is why it is called Firelihood, which is a contraction of fire and likelihood in English. So it associates several researchers at INRAE, including myself, Thomas Opitz, which is a statistician which is a specialist on extreme value theory, Jean-Luc Dupuis, and the other are different students who contribute to this work. Just to briefly give the context, we have talked a lot about fire behavior modeling with different types of models. This tool generally do not answer regional questions, and I added generally just at the beginning of my talk because of the previous presentation. But in general, they don't address this question. And there are still some important questions, which is that ignition patterns are not straightforward, I would say. So how can we predict where the fire will be? And the second question is when, which year, which week, which day. There are lots of fluctuations on all this stuff. And so typically people use a fire danger metric, and the most famous one is probably the fire weather index. If you look at trends over time, burn area tend to decrease with large fluctuations at the regional scale. FWI also, sometimes they reflect the variation, sometimes not. And at least it does not represent the right trend. Moreover, there are some seasonal bias. For example, if here it's the day in the year, the FWI tend to increase something like 2-3 weeks in advance with the actual fire activities. And if you look to a map, well, you will see that the observation are not a relevant, a consistent representation of the FWI map, just because here there is no fire, because there is no vegetation. So the idea of this work is to build a probabilistic model that will aim at reproducing these wildfire activity patterns at a regional scale. It was developed in the frame of a PhD student that now works from the Ministry of Agriculture and with Thomas Opitz, the colleague I just mentioned before. And the idea is to distinguish the occurrence and size and to see the fire at regional scale as a market point process. So the points are the fire ignition, and we predict the size based on a probabilistic approach. So the scale is the daily prediction, and on this version of the model, 8 kilometers. And it was developed in a Bayesian framework using INRAE and SPDE, which allows to account for spatial effect. So for those who know this kind of model, it's relatively similar to a generalized additive model, but it's much more flexible on the kind of distribution you can model and the force of the response function you can do. So the first component is what we call the occurrence model. So it predicts the number of fire larger than 1 hectare per pixel and day. So this accounts for both the ignition and initial spread. And this target of 1 hectare was taken because this is a target for firefighters. The idea is that they have to catch fire before they reach this threshold, otherwise it is called an escape fire. And so we just model this distribution with a Poisson distribution with a very simple explanatory variable here. And after we will add more, but from the first version of the work, we used only the FWI and the forest area. And we had some couple of temporal and spatial factors to account for the fact that these variables doesn't explain everything. For example, the data shows that there is a very sharp increase near 2003. So in this first model, we just put a basic threshold. Are we before or after 2003? And we have a spatial model based on SPDE, which allows to take into account the fact that regional probability of ignition, regional probability of firefighters to catch fire are different. And because we know that the FWI is biased seasonally, we add a seasonal component. So this, on the first hand, these terms can look like cheating because you help the model to provide good relationship. But if you go to the detail, I will try to convince you that it's not, and it helps to have a model that have better response on the important variable. So once you have the occurrence, you want to predict the size of the different model. And so we model the distribution of fire that you can get for different FWI and forest area conditions. So typically, we have a 3 exceedance threshold. So we predict the probability that the fire will exceed 10, 100, or 1,000 hectares. And beyond and between this threshold, we use a Pareto distribution. And for the last one, we use the general Pareto distribution, which allows for the fact that there is no fire that has an infinite size. And so if we look at the model fit, this left part is the occurrence model. So again, the occurrence is the number of fire larger than 1 hectare. Here are the response functions that we have. So to the FWI, this function means that when you move from a FWI of 5 to a FWI of 60, you have 50 times more fires that will escape 1 hectare. So both in terms of ignition and initial spread. Here, this is the weekly effect that was assumed. And here, what this says is that if for a given FWI value, your fire starts on the 30th of August, then you have something like 1.65 times more chance to get one fire than if it's in the beginning of June. So it's a way to correct the fact that the seasonal distribution of the FWI is incorrect. This one is more obvious. It's just the forest area. When you have no forest, then you have no chance to have a fire that escapes 1 hectare. It goes to a certain point, and then it decreases, just representing the fact that this area are less populated. And this is the spatial model I was talking about. So it takes into account of all the spatial residual. So these two can be somehow criticized because you will say, oh, you use some variables that are not really explanatory variables to explain your patterns. But if you think about not using them, it will mean that when you adjust your response function, you will take pixels from the 30th of August in this region, and you will compare the response function of a fire occurring at this period of the year in this region, which makes there is no chance that you have a consistent response function doing that. So this helps to have a nice response, and then once you have that in modeling, you can really model accurately the local patterns. The size component model, here represent here the probability to exceed a certain size. So of course we model only 1 hectare fire, so the probability is 1 for every value of FWI index. But if you take higher threshold, of course, the probability is lower. So for example, for 100 hectare, it's about 1% when you are in low FWI condition, and it increases to 10% when you are in high FWI condition. And same kind of stuff for wildland area. So the more wildland area you have, the more chance you have to have a large fire. So these were the response function. From this, we can simulate for a given day the probability in each pixel so these are the explanatory variables represented in very coarse classes, not a detailed map, but I think I did this on purpose to have a clearer idea of how these patterns will explain here the probability to exceed 1 hectare, and here a probability of a given fire to, once it started, to exceed 100 hectare. So here what you can see is that these probabilities are highly variable. Sometimes you are close to 5%, sometimes you are close to nothing, even on a very severe day. But still, these probabilities are very low, meaning that it doesn't mean that the fact that you have a red spot here means that you will have a fire. But so the process, what this reveals is that the ignition patterns and the chance to escape are highly stochastic, even if the probability are really different from an area to another one. So it can be seen as an objective map of the risk to get a fire, but in practice this is difficult to convert this in terms of ignition. For the probability to exceed 100 fire, you can see that it can reach some significant value. It can sometimes, in this pixel, it means that if you have one fire this day, it has good chance to exceed 100 hectares. Sorry. So once you have your probability, the idea is that you can do some simulation of potential fire activity because you can sample within your Bayesian model and also sample in the fact that the process is highly stochastic. So here you have your dates and your pixels, and for each of them you do one simulation where you have, in this case, one fire here and one other here, and with the size model you assess the size to this process. So taking one by one, a single realization does not intend to reproduce the observation. It has no interest. But when you start to aggregate this list, you can compare these simulations to observation to evaluate your model. So let's take an example with year 2001. If I aggregate my fire over the whole area, I can draw, these are the days during the season, and I'm looking at the 1 hectare fire. The orange, light orange, correspond to the confidence interval of my model, because I have hundreds of repetitions. So here it gives you the minimum and maximum values, so that you have 90% changes that the observation is in this range. And the dark orange corresponds to the average. So this is more or less the expected behavior for these days. And in black you have the observation. So here you have the coverage probability, which is the computation of how often black points are within the interval. And they are not that bad with respect to the 95% target, meaning that the model correctly represents the uncertainties. And also you can see that even at this daily scale, the numbers are not that bad predicted. I mean, we cannot tell exactly the number, but the range are relevant. And if you take the same data and you aggregate them on the week scale, now you can start to predict very correctly what's going on. So in this special case, the coverage property is lower than 95% by accident, but the number of points that are outside of the interval are not huge. So same for 10 hectare fires, 50, 100 hectare. So what you see is that the more you take higher thresholds, the lower the values are, and the larger the confidence interval are. But still, you can pretend to say something for fire at least until 100 hectares. Beyond that, for burn area at this scale, you cannot say anything about the burn area at the weekly scale. They are way too random. Okay. Just a visual evaluation of the performance of the model when you aggregate over a long period of time. So this is the modeled pattern of fire activity, of escape fire, 1 hectare. And this is the observation. So of course your map is smoother than the observation, but it reproduces accurately what you have. And in the case of burn area, again, the pattern is smoother, but in order, it correctly represents the spatial differences. Other evaluation, if you consider the temporal evaluation, now I aggregate my data at the yearly scale. So still in black the observation, and in orange the model prediction. What is interesting here is that we took only data until 2014 to adjust the model. So it means that this is really prediction. For this part, the model just have the weather data for 1 year and is able to correctly reproduce the observation. This is the seasonal trends that are correct. And same stuff for burn area. So overall, burn area of course, much larger confidence interval, but I mean, points are okay, except this special point in 2003, and I will go back to this point later. So it gives an idea that you can apply this model for, let's say, a weekly prediction. So here are I showed just before only a few seasons, but now we have all the seasons since 1995. So you can see that these patterns are well reproduced for all these years, including the one after 2014, as I said before, for which the model was not, the data was not used to fit the model. So same kind of stuff, but just looking at the last 10 years and the ones that were used for validation, for the validation, where you can see that the patterns are accurately reproduced. So when I first saw these results, I was really impressed by the ability of the model to predict the number of fire of 1 hectare, because I had in mind that this was something explained by local patterns of ignition and things like that. But if you combine the fact that there is ignition, but at the same time the effort of firefighters to catch the fire before they reach this threshold, you find something that is can be explained with very simple variables, just the FWI and the forest area. So from that you can look at what are the scale of stochasticity, what can be reasonably predicted and what cannot. So we have seen that when you aggregate over the whole area, things are relatively predictable until almost the daily scale. So the uncertainty are not too big, they are on the order of 10–20%. But if you aggregate on a shorter period instead of, on a shorter spatial scale, typically if you take the pixel scale and the daily scale, then you have ridiculous confidence interval. So you cannot say anything because at this scale, the problem you are looking at is too random. So for small fire, you can predict stuff, and the more you consider stuff such as burn area, it becomes to be complicated. So here I say that this correctly represents the stochasticity of the fire activity, and somebody could tell me with a better model you will have less stochasticity because you don't use enough explanatory variable to explain that. But if you look at the seasonal variation, so this is the weekly burn area average over more than 20 years. So in red, it's the observation, and in gray, the model. Sorry, it's not the same colors than before, but the observation are in the range, but you could say that a better model could more accurately predict this stuff. But if you start thinking of what they represent, this is the last week of July, this is the first week of August. And of course, there are higher wind in July than in August, but I don't think that they will never explain the fact that this is more than 3 times higher, just shifting from 1 week. So this simple example just explains that this oscillation really represents, for burn area, a stochasticity that is really in the pattern of the fire activity, and I don't think this is something we can ever pretend to model, so to reduce this uncertainty. Just a way to say that I think the range of this uncertainty correctly represents the reality. A second application, climatic projection, which was the original goal of all this. So if you take some projection of the FWI, so here we have 17 climate model for 2 scenarios, then you can run Firelihood for here 300 likely realization of fire activity, and you can compute metric to evaluate the trends. So here I take the number of fire larger than 100 hectare, which is an interesting threshold for us. So in orange, you have the yearly variation. So the dotted line corresponds to the mean of the model of the fire model simulation. So it gives you some kind of idea of how the climate changed from one year to the next one. Whereas the light orange explain what is the uncertainty related to the fire process for a given season. And then from that you can draw some trends. The problem is that if you work on this yearly number of fire, you have a large increase by the end of the century, more than 150%. But the uncertainty for a given year is really high because you have the climatic uncertainty in brown, represented here, which just tell you that the climate is not the same from one year to the next one. And in addition to that, you have the fire uncertainty. So in the end, you have more than 85% of uncertainty on your prediction, meaning that the yearly prediction is not something you can really pretend to predict because of this variability. So a way to handle this is, instead of working with yearly burn area number of fire, you do a running mean to work on the decadal number of fire. So of course, this decadal number of fire has lower variations, and in this case, the climatic variations become shorter and the fire variations become shorter, but they still remain important. At this scale, the fire randomness is almost as important, as the climate randomness from one year to the next one. The problem of this approach is that we lose all the extreme year, which is a very important aspect. So what we did for that is that in addition to the decadal mean and its trend, we added the value at risk at 90%, which is different from the value at risk which has been presented before, which is just a measure of a typical worst year within a 10-year interval. This is this curve here. So it tells you that in average you have 5 fire larger than this 100 hectare 1 year, but once every 10 years you have more than 10. And the next one is an interesting concept, is the expected shortfall. So it's a measure of what's going on for beyond this decadal return interval, because it is an average of what's going on between the decadal return interval and an infinite return interval. Meaning that when you have EV tail with a very catastrophic year like that, your brown curve here will represent this being much higher than the value at risk at 90%. And the interesting aspect is that we can predict this, we can compute the uncertainty around these two curves, and they are not that bad. I mean, the uncertainty are slightly higher than the trend, but they are not exploding, which means that it provides a way to anticipate the crisis year in the future. From now, I just presented the 100 hectares threshold, but we can also work on the other 1 hectare. So very few fire uncertainty at that scale. It can almost be predicted just from the climate. For burn area, the fire uncertainty is much higher. This was done with one climate model, but most of the uncertainty comes from the climate model you use. So here we use 2 scenarios, 1.5 in red and 4.5 in blue. And we show the results for the trend for the 17 models. So you see that there is lots of divergence between the different models. If we want to represent this in terms of partition of uncertainty, you have here the 4.5 scenario, here the 8.5. In blue, the model uncertainty. So this is just due to the climatic models that you use. In orange, the climate uncertainty, meaning the internal variability of the climate over the decade, and in yellow, the uncertainty associated to the fire process. So these uncertainties are really big, as you see, but most of the perspective of reduction come from the climate, so we hope that climate specialists will have a better consensus on the projection, if it's possible, I'm not sure. With the same approach, you can project on maps, which gives an idea of places where it's going to increase, and increase in the duration of the season lengths too. Third and last application. The interest of this kind of approach is that you can have a critical view on the index you are looking at. So here the fire weather index. So these types of behavior, which is the response of fire larger than 1 hectare to FWI, shows that values of FWI above 60 doesn't mean anything. So probably that the index is not really well designed. I mentioned before the temporal seasonal bias. In blue, these are the simulations done by Firelihood if you don't take into account the seasonal correction, the weekly correction. So you see that the blue one is close to the observation, except that it's shifted. So there is really a seasonal problem. And we have some good explanation for that, because if you take some measurement of live fuel moisture content and you compare them to the drought code, you can see that for constant moisture content, the corresponding values for drought code are not at all the same at the end of July, which is 400, and at the beginning of the season, which is 800. So this clearly means that the DC overestimated how the fuel desiccates over the season. I said that I will talk about 2003 again, and this is the good time to do it. So if you look at the performance of the occurrence component, well, you don't see any specific trouble with this year. The number of escaped fire was well predicted according to the FWI. But once you look at larger fire, here it's 10 hectares. Oh, I forgot to say that the very light orange corresponds to a 99 confidence interval. So it's really, you should have only 1 point outside of the light one for 100 values. So this is really unlikely. And so you see that even for the 10 hectare fire, you start to have some. And the more you look at larger fire and until burn area, the more you see that during the whole season, the prediction of our model underestimate the number of fire activity number. And so it's not due to just a few number of fire, it's for all the sizes. For all the size, here it's the distribution. I will not explain this curve. So for all the size above 10 hectares, the fire number based on the FWI response that worked properly for all the other years, we underestimate the results. And so the most obvious explanation for that is that the FWI is not well balanced to capture the hot drought that appeared in 2003 because it doesn't increase enough when we are in such condition. And we have a paper recently accepted that a small part of it is on this topic. It's the different response functions that we have to FWI for different seasons. And you can see that during the summer, when the conditions are really dry for vegetation, then the FWIs work really well. But at the beginning of the season, when the vegetation is not that dry, we have some kind of saturation, and that we found also in October. So, and at much lower values. So this highlights the fact that at this season, the FWI is high because of wind, but in reality, there is no fire activity because the vegetation is not dry enough. We already have a Firelihood 2.0 with some improvements. So now 2 kilometers resolution, the inclusion of plenty of land use and land cover variable, and a refined spatiotemporal model. So just briefly, we had a response to fuel rate, fuel type rating. So we used the fuel map done by ONF, and we can see that for burnable, flammable fuel types, you have 3 times more fire than in the ones that are not flammable for same FWI and same everything. You have the effect of the aspect. So when you are west or south, you have more chances than east and north orientation. We have the slope. So the slope can look somehow weird, but in fact, these aspects just reflect the fact that in region with very high slope, you have less ignition. This is the temporal trend. And one interesting aspect is that we have a spatial model for temporal trends. So when it's in red here, it just explains that the fact that over the last decade, it has tended to increase, whereas here it has tended to decrease. So you can see that this overall decrease that you can see here, a very sharp decrease after the 2003 crisis, is not well spread over the territories. The size model, the corresponding size model for 100 hectares again. This time the slope has a much obvious effect because here we just look at the probability for a fire that has already started to exceed 100 hectares. And so in this case, the more slope you have, the more probability. We include a spatial model, which is much coarser than the one we have for occurrence. But it highlights the fact that for the same FWI, same forest condition, same everything, you will have much more chance to exceed 100 hectares for a fire that has started than in other places. And so here you can see that in the center of Corsica, the probability of an escape fire to exceed 100 hectares is higher than in other places for the same FWI. And so if you run the model, then you can build a 2-kilometer resolution occurrence map. So this is not exactly an ignition map, because it includes the capability of firefighters to catch the fire before it exceeds 1 hectare. But I think it's really informative because it gives a good idea of where you're going to have some trouble. And if you look at that, it looks like a smooth version of the observation. And you can see that you are able to estimate a probability of start of escape fire over a long period of time, even if you never saw any fire in this location. Last slide. We used the fact that we were at land use and land cover variables and fire weather index and this or other temporal change to do some kind of attribution to what explained the differences between fire patterns in between the 90s and for the most recent period. And what we saw is that if we only rely, well, the recent present is something like 40% lower than what was in the 90s. But if you only consider the effect of fire danger that has increased a lot over the period, you should have an increase of 55%, 54%, meaning that the FWI has really increased over the time. So the land use land cover variables that were shown before explain the spatial patterns that you observe. But what we show here, it's a hard zero, is that it doesn't explain at all the trend. So I think this is an important aspect. They explain the patterns that you observe at a given time, but they do not explain the trend. And so the other trends are mostly explained by change in prevention and fighting. And what is interesting here is that we can do some specialization of this. And you can see that there is a huge reduction in Corsica and in the west of the basin, in the east of the basin. But in this region, there has been some increase. So it really raised the question about how the means are disseminate over the territory and can ask relevant question, I think, in terms of the evolution of these patterns. To conclude, we think this statistical framework is very suitable and adapted to fire activities in France because with two very basic variables, we were able to reproduce quite well the patterns with this methodology. There are potential applications for operational because the prediction on the weekly scale are not really stochastic, and we have this objective map of escaped fire probability and probability to exceed a certain threshold. An interest of that is that for projection and any other application, the metrics are additive, number of fire activity, so you can aggregate them over time and space very easily. It provides insight of explanatory variables. I talk about the ONF fuel map, which has a good response in the model, the FWI and its limitation. And I finish with the perspective. So, as I said, we have another paper accepted on this topic, and I think it's a really interesting idea, even if I don't have the time to give so much detail. But the idea is that instead of adjusting the different components of the model separately, you adjust them together with interaction between size. And the idea between that is that you have lots of small fire that gives you a good idea of the pattern driving a small fire, and you have less information of larger fire because you have less observation. And by looking at spatial patterns in interaction between this scale, you can adjust and inform your model for larger size from your smaller size. So I think the idea is very interesting and it works well. Okay. Another application is an inclusion of this model in a forest sector model. So because you can simulate your fire activities, you can simulate the impact that it will have on timber production and price and supply of industrial woods and things like that. So this paper is under review. But there are other applications to evaluate cost, insurance, maybe related to the application that was presented this morning. Other perspective, we are a PhD just starting by the Jorge, the one who did Firelihood 2 in master. He will go on with a PhD to work on the refinement of the fire danger component this time, using the concept of fire weather type and doing specific work on extreme value based on extreme value theory. There is the opportunity with this general framework to test lots of indices that can be used or proposed for operational properties. We can change the scale. We can move to the hourly scale if necessary. If the data is available, we can change the spatial scale too to understand better the response, the shape of the response. This approach can be hybridized, I don't know the right word, but with a more physics-based approach. Typically, we can take the occurrence model and link it with what has been shown before to create a burn probability model based on contour. And I think Michele Salis will probably present something like that just after. We have several postdocs in a fire project that's just starting. One is on the application of this methodology to the other region in Europe. So the first one will be the west of France, where you have a good database, but there will be other applications to other countries. So if you have a fire database, don't hesitate to contact me. There is a second postdoc on the development of the early warning system. So it's related to the work on extreme values that will be done in this PhD. And the last postdoc on this project is to build a fuel map based on LiDAR data, because there is a national flight for airborne data. And we will convert this in a fuel map, and Firelihood will be a good tool to test the effect of this fuel map on actual fire activities. Thank you. There is a website if you want the update on Firelihood.